Good afternoon, everyone. Thank you for joining this live case study. And today we are going to discuss the Rayleigh damping parameters. In the case of a gravity dam, we will see how you can derive them from the frequency of your error and frequency analysis. So for today, we are going to use as a base of our demonstration a gravity dam example. We have a couple of tutorials online dealing with this gravity dam. One of them is called the response spectrum analysis of a gravity dam. There is also the transient analysis of a gravity dam and the Rayleigh damping of a gravity dam. So all these three are basically using this model as a base, and that's also the example that I'm going to today for the discussion. So during this session, obviously we are going to do some modeling. So we will generate the foundation and the dam itself in terms of geometry. We will assign some material properties that are basically listed on this table. So we keep everything linear elastic. We will apply some constraint on the side and the bottom of the model. And we will also assign the dead weight, which will be acting only on the dam. So that's why we will consider a massless foundation for this example, because by assuming a massless foundation, the wave speed becomes infinite and the excitation is applied at the dam at the same time as it is applied at the bottom of the model. So of course, this assumption is for simplicity with this specific examples, which target to show how to perform eigenvalue analysis to determine the Rayleigh damping parameters for the dam, which can be seen as a preparation for a transient dynamic analysis. But in reality, the foundation is not linear elastic and certainly not massless. So if you want to go for more realistic transient dynamic analysis results, it's better to use a mass in the foundation. But for today, we keep things very simple. I just want to highlight the options of deriving the Rayleigh damping parameter from DNI. Let's say a few words about the Rayleigh damping. So when you perform a transient analysis of structural models using Rayleigh damping, the damping matrix, as matrix C, is calculated as a linear combination of the mass matrix M and the stiffness matrix K, where A and B, the two parameters here, are the Rayleigh damping parameters related to the mass matrix and the stiffness matrix, respectively. As described in the book of Chopra, the Dynamic of Structures Theory and Application to Earthquake Engineering, damping ratio depends on the Rn frequency F of the structure and on the Rayleigh damping parameter E and B. So basically, you can write for a mode N the damping ratio as follows, as a function of the frequency, Rn frequency, and A and B. Of course, if you express you can also express the function as based on the angular speed, which is basically 2 times P's Rn frequency, and then this equation results as follows, which basically is the equation of the damping ratio depending on the damping parameter A and B and the angular speed. If we put that in a kind of graph, basically we can see the here on the right, you see on my on the right side of my slide, the variation of the model damping ratio against the angular speed. So in blue, basically you have the part coming from the stiffness, and the part in red is coming from the mass matrix, and basically the red is basically your damping matrix, which is a linear combination of your mass matrix and your stiffness matrix. If we want to determine the Rayleigh damping A and B from specify a damping ratio for a mode I or a mode G, based on the formula of Chopra that we have here, but then written for a mode E and a mode G, we can put that in a form of matrices, and basically the two unknown are basically A and B. In Diana IE, you can calculate the Rayleigh damping parameter based on this equation by choosing a set of damping ratio, which are basically on the right side of the equation, and from Rn frequencies, which are linked to the angular speed here. I remember you that it's 2 times Pf. So the set of damping ratio are defined by the user, while the Rn frequency, Fi and Fg, can be explicitly specified, determined by providing the corresponding Rn mode. So for instance, mode 1 and mode 3, or based on the Rn frequencies specified by a cumulative effective mass percentage in the global XYZ direction, which is equal or higher to 90%. In case the requested cumulative effective mass percentages cannot be reached for the calculated number of Rn frequency, the second frequency is the highest calculated Rn frequency. So these are the three methods that are available in Diana. I will show you how you can use them. But first, what we need is basically to get the Rn frequency of our model and identify which one we are going to use. So first, I'm going to set up the model. Then we will perform a Rn frequency analysis, look at the different Rn frequency and their cumulative effective mass. Then we will choose the frequency that we are going to use to determine A and B damping parameter. We will do a non-calculation based on that. And so basically by injecting our frequency in this matrix and defining a damping ratio. And from that, we will derive A and B. And then we will see if our uncalculation is in good agreement with what Diana find as a derive from the Rn frequency analysis for the A and B parameter. So this is the challenge of the day. But first, let's start by the modeling part. So I'm going to open Diana, which is already on my screen. Here we go. So I think you are all familiar with Diana environment. This is a very, very standard, I would say. So basically, the first thing we need to know to do is to define a new project, as you all know by now. So I'm going to call it Rayleigh. I need to give it a name. I have already a directory for our session of today. So I'm going to use this folder. Then for the analysis, we are going to perform structural analysis. So I don't need to activate any other options. The model is 3D. The model size is 1 kilometer. As you know by now, this is basically the diagonal of your modeling box or modeling plane if you are in 2D. So you should make sure that it's big enough to accommodate your model. And for the default measure, I go for hexaquad dominant, and I keep things linear for the mesh order. So Diana is going to start with the right settings. Here we go. And the first thing I'm going to do is basically to define a 2D section of my foundation that I'm going to extrude later in a third direction. So I have an Excel file that I can show you over there, which give me the coordinate of the section of my foundation as well as the dam. So that's what I'm going to use to make it relatively fast. There are different methods, and for this one I'm going to use basically the coordinate. So I open the polygon sheet action box. I call it foundation without typo, preferably. For the method, I choose coordinate, as I mentioned, and I'm just going to copy the coordinate point that I have in my Excel sheet over there. I'm going to adjust the size of my model, and immediately you see a preview of my foundation cross-section. So keep in mind that nothing has been created yet. You see that under the shape on the left, there's nothing. So until and unless you click create, nothing is created. So I click on create, and now you see that I have a shape called foundation that have been created. I'm going to extrude this foundation along the X direction. So I'm opening the extrusion feature. I select this shape, and I'm going to give it an offset of -700, 0, 0. And I fit it to the size of my screen, and you see a preview of my foundation. I click apply, and then my shape, which is now a solid body, it was a sheet, now it's a solid body, is listed under the geometry tree under shapes. So this is one part of the model. Now we need to define our dam, and I'm going to use the same method. I'm going to define as a polygon sheet the 2D section, but I'm going to extrude in a third dimension. And then I will intersect this shape with my foundation to get rid of the unnecessary part, I would say. So again, I open the polygon sheet. This time I call it dam. I go for the method coordinate, and again, I specify my 4 points. So again, this is one way of doing it, just to illustrate that you can copy paste basically coordinates to diagonally, but it's not the only one. I mean, there are many ways to generate these shapes, but let's say that this is the one I choose for today. So you can see a preview of our dam shape. I'm going to click on create, and then I have a dam sheet which is created there. I'm going to extrude it just like I did for my soil. I select this face, and now I'm going to extrude it in the Y direction with an offset of 560. I adjust the size. You see the preview button, the preview of the model, and you see that my dam has some extra part which are going to crossing the foundation, but I'm going to remove later in the next action. So first I click apply, and now I have my two shapes. And what I'm going to do now is I'm going to subtract basically the foundation, do a subtraction between the dam and the foundation to remove the part of the dam which are basically crossing the foundation. So I click on the subtract operation. My target is a dam. The tool is the foundation. And basically I want to subtract. I want to keep the tools. And I click apply. And automatically, Diana does the subtract operation and removes the unnecessary part. And I end up with my foundation and the dam. I can change the color to make it a little bit more realistic. And here you see our model. It's very simple for this analysis of today. We keep everything simple. So next to that, I'm now going to assign my property, which are basically a linear elastic property. So I go to the shape property and I start with the dam. I go for structural solid, and here I define my material, dam. I'm going to choose for the concrete and masonry, linear elastic. And I'm going to enter my material property. Let me find back the value. So for the Young's modulus, it will be 3.2 E10, 0.2, and 2,400 kilogram per cubic meter. I click on apply. I repeat the same operation for the foundation. The element class is structural solid. I create a material, which is soil and rock, linear elastic, no aspect to include. And over there, I go for 8.9, 9, 0.2, and the saturated density is 0. So I consider the foundation as massless, as I have explained already in introduction. So I click apply. So I see that under my geometry tree, I have two materials, the dam and the foundation. I can make sure that the assignment is done correctly by passing my mouse on top of my foundation set, and I see that my foundation is a shape class body, is a body type solid body, and it has a material foundation associated to that. If I do the same for dam, and I also see that there is a dam material associated to my set. You can also color the geometry by material color. But since my colors are pretty close to the one I use, you won't see much difference. Only the foundation will be clearer. We can actually do that. It doesn't harm. That's also a way to check that your assignment of material or other properties is properly done, so that you see that the part of your model carries the right color, which is associated to your material. So next to that, we need to define some boundary condition. So I'm going to do that right away, starting with the condition on the X face, which will be part of a set BC. I select the face, this one, and this one, and I constrain the X direction. I click create, bring that back to the center. Then we are going to do the same for Y, and BCY. So I select this face and this one. But then now I constrain the Y direction, not the X. And finally, BCZ, which is for the bottom face, for which I constrain the third direction, which is along the Z axis. Here we are. So now I can check also under the geometry tree that under support, I have my set BC, which constraint in my three conditions along X, Y, and Z axis. So we are almost there. The last thing I want to include is a dead weight, and because we consider massless foundation, the dead weight will be only acting on the dam. So I define my dead weight. Without typo. Click apply, and then create, and then it's all good. So if I go to the loads under geometry tree, under the cases, I see that I have my dead weight, which is created. So my model is almost ready. The last thing I need is basically to define some mesh property. So I go to the mesh property and I select shape, and I go for element size. I select the two body. Now the two, and I go for a size of 40 meter. And as I mentioned in the property at the start of the project, I can also mention it here. I go for hexaquad dominant. If you change something here, it's going to overwrite what you specify at the start of your project. But now I just keep the same, so it's going to use the same. And if I don't specify anything, it will be the hexaquad because I specify that at the start of my project. I click apply, and then I'm going to generate my mesh, which will be very, very coarse, as you can see, but which is good enough for this demo. So now we are going to set up a structural eigenvalue analysis. So first we add a new analysis, that I'm going to rename as eigenvalue analysis, and I'm going to add the structural eigenvalue. Let me expand a little bit. So I'm going to edit the free vibration property here. And in this property, the dead weight load is considered. So I use a geometric stiffness matrix where I use the dead weight to calculate the linear elastic field. For the eigenvalue, I'm going to ask for the first 10 eigenmode. And that's it. And then I basically press run, and Diana is going to compute these 10 modes. And if I expand my message window, you see there that the 10 first error frequency of my model are listed there. I'm going to go to my working directory over there, where you see that there is a Rayleigh project that has been created. And in this project, you find the output file. And this output file contains more information about the error frequency, because what you see in the message box is basically this part, but there are much more, including, for instance, the cumulative percentage per direction X, Y, and Z. This is what I'm interested to determine which frequency will be used to derive my Rayleigh damping parameter. So we are going to use this information here to determine this mode. So let me get back to my presentation. Okay, here we go. So as you remember, we were at this stage where basically we need to identify the frequency that we are going to use, the RN frequency, and then to specify some damping ratio. And then from that, we will be able to derive A and B. So I have copied the output of my output file from the RN analysis for the X, Y, and Z direction. And from that, I can see that for the X direction, so I have the first mode, and the mode 6 is the lowest mode with a cumulative percentage which is above 90%, where for the Y direction, this is for the mode 2, and for the Z direction, this happened for the mode 6. So based on that, basically the two frequency Fy and Fg, if I refer to the Chopra equation that we can use, are basically the first one, which is 3.25 Hertz, and F6, which is 7.85 Hertz. So if we basically use this value, we can, I forgot to add something, which is also important to take into account at this level before we inject, let's say, this value. It's good to note that the choice of the frequency, Fi and Fg, should also depend on the base acceleration used in the transient analysis. As I mentioned, this example is a part of three cases, and one of them is a time history analysis of gravity-dam, where, as the title said, we perform a time history analysis of gravity-dam, and in which we use an accelerogram. So this is the accelerogram we use in this analysis, and using a discrete Fourier transformation, we obtain basically the following diagram, where we observe that most of the energy content of the earthquake is between somewhere here, which is, let's say, 0.5 Hertz, and somewhere around 4 Hertz. So it means that Fi and Fg, the chosen frequency used to derive damping parameters, shouldn't be filtering out this part of this band. So if we look at the frequency that we found out, so F6, for instance, which is 7.85, so it's somewhere over there. So we are basically outside this band of 0.5 to 4 Hertz. So we are good. But for F1, which is 3.25, 3.26, we are somewhere here. So we are within this band. And we don't want to filter out the frequency of the input signal above 0.5 Hertz. And so we should use smaller value for the damping ratio. So basically for this parameters here, for the right-hand side of our equation. By default, Diana IE assume 0.05 damping ratio for both IAG if we don't specify anything. So here in that case, since we want to use a smaller value, we are going to use for the first mode 0.025, and for the second one, the mode 6, we keep 0.05. So having said that, if I basically inject my frequencies, but in terms of angular speed, if I multiply that by 2p, then I get my angular speed for mode 1 and mode 2, mode 6. Yeah, it should be a 6 here actually. Then I can write my formula, which was there. I keep going forward and backward. So this formula here, I replace the angular speed by their value and the damping ratio by their value. So I come to this system where A and B, the damping parameter, are basically my unknown. And I can solve this set of two equations very simply. I come to the value for A and B as follows. So A is equal to 0.21089 and B is equal to 0.00193. So these are the value that I derive manually from my my RN frequency analysis. So we did that, by n calculation. So first we perform a RN value analysis, and from this RN value analysis, we identify the two frequency that we are going to use. We also play a little bit with the damping ratio to make sure that we are not damping out too much based on our earthquake signal. But this actually can, these parameters can be derived directly by Diana from the RN value analysis. And that's what I'm going to show you, how to activate that. So I go back to my Diana, and now I'm going to use the same analysis, but I'm going to add an extra settings, which basically will be to derive or to calculate the Rayleigh damping parameter. So if I click on the structural RN value, right click, I click add, you see that I get this menu, calculate Rayleigh parameters. And as I mentioned earlier, you have different methods, whether you explicitly mention, you give the modes, or you go for the effective mass. We are going to go for the effective mass. I click there. Here you have the two damping ratio. As I said, by default, Diana use 0.05 for both damping ratio. But as I explained, we want to use something smaller here. So I go for 0.025. And for the second one, I keep 0.05. And basically, for the effective mass, you go for something equal or above of 90% in the three direction. And that's it. And now I'm going to rerun the analysis. And as a result, I will get my RN frequency. And it will also tell me which frequency has been used and the value of the damping parameter. So I go there and I click run. And here are the results. So you see that again, I have my RN frequency that are listed there. And you see that we have some extra information that appear here, which are the Rayleigh damping coefficient, so the frequency, and the damping ratio. So the frequency used are 3.18, which is a mode 1, and 7.76, which is mode 6, and the mass factor A and stiffness factor B, which are basically our two damping parameters, which are 0.2157 and 0.001958, which is in good agreement. If you remember our end calculation, for A, we were getting 0.21089, which is in good agreement. And for B, we were getting 0.00193. We got 0.195, so it's in agreement. So you see that instead of doing that by hand, you have the option in Diana to calculate your Rayleigh damping that you can later on use in your transient heat analysis, for instance. Of course, this example is relatively simple because the idea is just to illustrate based on calculation and based on the option in Diana that you can get a good correlation. But you see that with eigenvalue analysis and activating these options, you can also, of course, go for a different method, the explicit frequency or RN mode, we choose for the effective mass. Then you can derive your damping parameter that you will use in your transient heat analysis. I have taken these results to my presentation. Let me get back to that. And if now we substitute the obtained value A and B, and we use our damping ratio 0.025 and 0.05 in this equation, let me get back to it. So in this equation of the damping ratio, we can plot basically the curve, which is the damping ratio versus the frequency. And what we can see on this graph is that between approximately 0.8 Hertz and something like 7.8 Hertz or 7.6, there's not overdamped. So for the calculated Rayleigh damping, so it means that the main frequency of the input signal that we are going to use in our time history analysis are not being filtered out due to too much damping during the transient analysis. So the choice made were basically relatively good. So as you can see, I mean, it's relatively easy to activate these options, and it can save you some time in the sense that you don't have to do manual calculation. In such an example, it's interesting to do that because we can see if we have a good agreement. But keep that in mind. I mean, you can derive the Rayleigh damping of your model from the eigenvalue analysis in Diana, and you have the choice between three approach. Today we discuss cumulative mass, but this is something which is available, and you can use it if you need to derive the Rayleigh damping parameters. So this is it for today presentation. Let me see if there are any questions. Do I need a special license to activate that? No. I mean, if you have access to the structural eigenvalue, basically this option is just a standard option in this module. Of course, if you have more questions, feel free to ask them by email eventually later. Yeah, the reference I was mentioning for the formula is the book of Chopra, which is, let me see, what was the title I said? I had the ref. Just give me a sec. Yeah, so it's Dynamics of Structure, Theory and Application to Earthquake Engineering. And yeah, it was a 2007 edition. Okay, so one more thing before I end up this discussion. Just want to bring to your attention that in the coming weeks, months, we have a good number of events. For the one who are interested into seismic analysis of structure, on 11 and 13 of October, we will have a two session courses, two session of 2.5 hours. And this is a paid course. You can still register. We still have few seats left. So do not hesitate to register if you are interested. And we will also have, again, a nonlinear behavior of reinforced concrete course, which is our regular course that we give every semester, trimester, sorry. And this one will be from November 28 until December 13. And this is a 6-module courses, and it covers all the aspects from intro to Diana, modeling of concrete, heat analysis, younger learning of concrete, nonlinear method. So it's quite a complete training. And next to that, in November, from 15 to 24th November, for the one who are not familiar with finite element method and want to get introduced to this method, we have an introduction to finite element analysis. It's a 4 session courses where we cover the basic aspect of the finite element method and the finite element analysis. So keep an eye on our website. There are plenty of events. And yeah, I hope to see you in one of these upcoming events. And of course, there will be more free webinars and live demo also in the coming months. So I wish you all to have a pleasant end of the day or mid-afternoon, depending where you are on the globe. And I'm sure that we will be in touch in a close future. Thank you very much for attending this session, and wish you all a fine day. Bye.